Good afternoon. Today we're going to look at the exponent laws and how to combine them together. Now the not the exponent laws, the logarithm laws. Logarithm laws, the sum of two logarithms can be replaced with the logarithm of the product of the arguments. The difference of two logarithms can be replaced with the logarithm of the quotient of the arguments. And then a times log base b of c, we can shake up the exponent, the number, the coefficient in front, so it becomes the exponent, or we can go backwards. Now, since these are identities, we can go replace two terms with one, or we can replace one term with two. We can go backwards or forwards in this. So those are what we went over yesterday. Now here we want to write these in terms of log x, log y, and log z. So this is the opposite. We're blowing this up. Here we have the log base 10 of a quotient, x times y over z. The difference law of logarithms, or the quotient law of logarithms, I should say, says I can write this as log x times y minus log z. And then looking at this term here, we have the logarithm of a product. I can replace that logarithm with the sum of two logarithms. Okay. So we are exploding this up. We're going backwards from what we talked about yesterday, although we are doing it with the same rules. Now, the first thing that I'm going to do when I see something like this, log base 7 of x to the 1/3. Okay. Now, what I see here, since I want this as log x, or in this case log base 7 of x, I'm going to shake down the exponent. So log base 7 of x to the power of 1/3, that is the same as multiplying 1/3 by log base 7 of x. I'm going to do something similar here. I'm going to write this as log base 6 of x to the -2. I got my log base 6 of x, I just got that -2. So shake down that -2 in terms of log base x. That's our answer. Now this one here, a little bit more complicated. We have the logarithm of a quotient. Let's write that as the difference of two logarithms. We have log x cubed minus log y, and then I'm going to write this as z to the 1/2, and that 1/2 only is applying to the z. I now have here, I have the product of two logarithms. So I'm going to, and in brackets, because if I don't do this, I'm going to mess it up. I need to have the brackets of the difference of two logarithms. And then the final step is those exponents. I don't want those exponents on top. 3 log x minus log y minus plus 1/2 log z. Now what I've done here is I've expanded the -1 that's outside the brackets in and dropped them. So I could have just left it easily as brackets there, not an issue. Now simplify and then evaluate. So here we have the product. We have the sum of two logarithms subtracting this guy at the end. There are several different ways of doing this. What I first want to do is I got to deal with this 2, because I have the sum of a logarithm plus two logarithms. I don't like that. So I got to deal with that 2. And I'm going to do that by shaking it up. Now, one of the things I like here, I can think about this guy as -1 log base 6 of 2. So I can also shake that -1 up. And now what it does here is I've got the sum of 3 logarithms. Well, what I can replace the sum of 3 logarithms with is the logarithm of the product of those 3 logarithms. So we end up with log base 6 of 24 divided by 2. And we cannot evaluate that. Oops, nope, never mind. I lost a square, shook it up, and then forgot to put it up there. Sorry. Okay. So now we have 8 times 9 is 72. Divided by 2, we have 36. Power of 6 that gets me to 36 is 2. Don't lose things. Now, to evaluate something like this, okay, we have log 7, 7 times 7 to the 1/2. Okay. Well, I could just basically do this, log base 7 log base 7 of 7 plus log base 7 of 7 to the 1/2. I can then shake down my 1/2. Now what this does is, we could gather like terms whenever we want to do this. We have log base power of 7 that gets me to 7 is 1 plus 1/2 times 1. So we have 1 and a half as the answer. So, and that's another way to evaluate. Now over here on this one, on the left, I don't want to evaluate log base 6 of 8. I don't know that number. I know it's slightly bigger than 1. But by gathering or by using the laws of logarithms, I'm able to simplify that down. This one here, I'm going to do the same thing as before. I see the difference. I see coefficients in front. And I'm going to imagine a coefficient of -1 in front there also. So log base 2 of 12 squared plus log base 2 of 6 to the -1. So I shook the exponent or the coefficient -1 up, turned it into a plus log base 2 of 27 to the -1/3. Again, with the reason that this allows me, now I got pluses. Now I can just do multiplication all at once. Log base 2 of 12 squared times 6 to the -1 times 27 to the -1/3. Evaluate, we have 144 times 1/6 times 1/3. 144 divided by 18 is 8, so log base 8 of 2. The power of 2 that gets me to 8 is 3. Now, here we want to simplify these. We want to go, again, here we have we have variables in here, but the same principle. What I see here is, this is kind of annoying. I'm just going to write this as 5 over 2. Instead of 5 log 7 times of x divided by 2, that's the same as 5 over 2 times log base 7 of x. I'm going to do this slightly different from before. I'm going to deal with these two first. Log base 7 of x squared times x minus, now I am going to shake up that 5/2. I have to. Okay, because I do not have a law of logarithms that has a number between them. I only have the logarithm minus a logarithm, so I have to shake up that exponent. In this case, I didn't shake up a negative. Fine. Now I have log of x cubed over x to the log base 7 of x cubed over x to the 5/3. Performing your exponent laws on this, you have log base 7 of x. I'll write 3 as 9/3, so we end up with log base 7 of x to the power of 4/3. That is the simplest form of this one. Now, the fact that we have a binomial and a trinomial here does not affect this. We have the difference of a logarithm. Difference of two logarithms. I'm going to take the difference of two logarithms and I'm going to write them as the quotient, or the logarithm of a quotient. Now, generally what I like to do is, can I reduce this? I can take a 2 out of the top guy. I can factor the bottom guy like this. We can reduce that. Log base 5 of 2 over x plus 3 if x is not equal to 1, because we have reduced and there still is a non-permissible value within that expression. Now the last one comes directly from a diploma. We are going to basically talk about our unit circle. Unit circle, that's 1. Not a trig question, this is just a basic log question going back to what we know. We have points, square root of log A and the square root of log B is the point. So if we have our unit circle, this length here would be the square root of log A, because that's our x coordinate, and that length there would be the square root of log B. Pythagorean theorem states a squared plus b squared is equal to c squared, or a, square root of log A. I'll use different variables here. M squared plus n squared is equal to O squared, just because I already used A and B. So log A, square root of log A squared plus the square root of log B squared, that will be equal to 1 squared. We have log A plus log B is equal to 1. Well, we're not quite there yet, but now I have the difference. I have the sum of two logarithms. I can replace everything on that left-hand side with the logarithm of the product. Okay, well, we still need to get A by itself. Well, what I see here is I see logarithmic form, turn it into exponential form of the statement, and then solve for A. Divide both sides by B. A is equal to 10 divided by B. There is that. Now, obviously, that is not, sometimes it's not going to be readily apparent to you. That's what you have is you have to think about Pythagorean theorem. Okay, what can I do? Can I work my way down? I've got to get that A by itself, and that's the way that we're going to do that. So again, I suggest that you take a look at the questions in the textbook on page 400, and we'll go over those during class.